dear students, I'm Meghamala, working as assistant professor from EC Department, Institute of Aeronautical Engineering. And today I'm going to share something about synthesis of asynchronous sequential machines. So basically, in the previous classes, we have discussed what are the sequential machines and types of sequential machines. In the sequential machines, we have synchronous and asynchronous as well. So synchronous sequential machines are the machines where it deals with respect to the time. Whereas the asynchronous sequential machines, these are the machines where they go without the, not with respect to the time. And now, we will discuss about the synthesis, okay, the design part of the asynchronous sequential machines. In the previous classes, we have discussed about the analysis. So in the analysis, by considering few examples, we have discussed how the analysis part of the synchronous sequential machines and as well as the asynchronous sequential machines went on. And now the sequential machines, asynchronous sequential machines, synthesis of asynchronous sequential machines are nothing but basically asynchronous sequential machines is a sequential machine without flip-flops. So asynchronous sequential machines, you have to remember the word, or else you have to ponder on this word, asynchronous sequential machines. So synchronous sequential machines, they consist of the memory elements. Like we all know the memory elements, flip-flops, latches, etc. Right? So the synchronous sequential machines, they do consider the memory elements. That means the synchronous sequential machines consist of combinational circuits along with the memory elements. But the synthesis goes on with respect to the time. Whereas the asynchronous sequential machines are nothing but they don't consider any memory elements like flip-flops. So these are the machines, the sequential machines without flip-flops. Flip-flops are nothing but the memory elements. They store one bit of memory elements. So these are like asynchronous sequential machines are the machines. They don't consider any sequential machines. That means what? They don't consider any kind of the memory elements, nothing but the flip-flops. So asynchronous sequential machines are constructed by analyzing combinational circuits with feedback. So this asynchronous sequential machines, they do consider the combinational circuits with the feedback. Okay, we can see in the synchronous sequential machines as well. There we have the feedback with respect to the memory element. Whereas here also in asynchronous sequential machines, we do have the feedback analyzing the combinational circuit. Okay, and then coming to the assumption. So assumption goes like this. Only one signal in the circuit can change its value at any time. So here the assumption can be made like this. Only one signal in a circuit. Okay, in the circuit, only one signal. For example, if you have to execute multiple signals, but here only one signal in a circuit can change at its value at any time. So in the circuit, out of the multiple signals, only one signal can change its value at any time. Okay, not with respect to the time. At any time, it can change its value. That is what we are saying, that it is an asynchronous sequential machines. If you compare it with the sequential machines, what happens is only at definite time period, only at definite time, we have to change the signal. Okay, there is a possibility of changing the signals only at a particular time. But whereas in asynchronous sequential machines, out of all the different signals, one signal can change its value at any time. Okay, that means what? Not with respect to the time. At any time we can able to change. So the golden rule here follows this. Only one signal at a time can change its value. So one signal at a time can change its value. One signal at a time can change its value. This is nothing but the golden rule that we can see in the asynchronous sequential circuit. And now the asynchronous sequential machines, okay, are used when it is necessary to keep the information about a state but no clock is available. So you have to concentrate on this particular word, no clock is available. Why here no clock is available? Why? Because here we are not using any sort of memory elements. So these are the machines where it takes, or else the execution or else the assumptions can be made not with respect to the, not by considering the, so what do we say, the memory elements. So that's the reason when there is no memory elements, obviously no clock signals are assumed. So here the asynchronous sequential machines are used when it is necessary to keep the information about a state. So if and only if it is necessary to keep some information about the states, okay, about the transition of the different state from one state to another state, always remember that no signal, no clock signal is available. If you transit a signal, or else if you want to change the state from one state to another state, remember that there is no need to have the clock signal. Why? Because they run without the memory elements. There is no use of flip-flops and latches over the asynchronous sequential machines. And all flip-flops and latches are asynchronous state machines. So here in the all flip-flops and latches, as they don't consider in the synchronous sequential machines, so here they are nothing but the asynchronous sequential machines. All flip-flops and latches are not to be considered, are not in consideration in the asynchronous sequential machines. So useful to synchronize events in situations where metastability can be a problem. So here, if you are considering any sort of memory elements like flip-flops and latches, you may have to see the consequences that metastability can be a problem. So here, unless and until if you are not using any sort of memory elements, the storage elements is not to be considered, then it is well and fine. Okay, you can transit the states, you can transit the different states among the different states, but if there is a chance of considering any sort of memory elements, but you have to face a consequence saying that the metastability can be a major problem. Okay, so useful of synchronized events in situation where the metastability can be a problem. You can see a metastability problem. And to analyze the behavior of a asynchronous circuit, we use ideal gates and summarize their delays to a single block with delay. Okay, so here in order to analyze the asynchronous machines, so what do we do is we use usually the ideal gates. Okay, in order to analyze the asynchronous machines, we use the ideal gates. And what do we do in the next is we will summarize. Okay, we will summarize the delays. That means what? We will concentrate about the delays. With what sort of delay the input is taken out to get the output. So we do consider the gates, ideal gates, and then followed with the summarization of the delays. Okay, delays to a single block with delay delta. So this is how we are presenting the delays. And now if you observe here we have considered the SR latch. Okay, set reset latch. So this is a set reset latch block diagram, and here reset and set and the output QA. So here you see the delay gates. Ideal gates are, what is this? NOR gate followed with the one more NOR gate, right? So NOR gate and NOR gate with the summarized with the delays. So here the delays will be summarized. The delays are summarized by considering the ideal gate. So here, as we have considered the ideal gate, when the gate is an ideal, that means what? It mates to 0. So this is just analyzed based on the synchronous machines. So saying that we use ideal gates. These two are the ideal gates where we have to summarize the delays followed with these two gates. So here if you observe, by using delay gates, okay, by using delay block, we can treat Y as the current state, Y as the next state. So here, Y as the current state and next state. So here if you observe, see, this is Y as the current state and the next state. Okay, so this Y we got from the one of the output of ideal gate, whereas the current state is nothing but by summarizing the delays. So after summarizing the delays, we got the current state. Okay, then thus we can produce a state table. So here, thus we can produce a state table where the next state Y, so this is the next state Y, depends on the inputs and the current state Y. So here the next state y, this depends on the current state y, okay, and as well as the inputs. So here the next state always depends on the current state y. Small y is the current state y, and as well as the inputs, okay, and as well as the inputs. So if you observe here, this is the expression that we got for the next state. So this is a next state. Y is equals to capital Y is a next state, and this is a present state. So the next state we will be getting the, how can we get the next state? Next state depends upon only on the inputs and as well as the present state. So this is what you have to remember. So y is equals to r plus s plus y. That is what, right? So r plus s plus y. Okay, all together plus is nothing but the OR gate. We are using NOR gate. NOR gate means OR plus NOT. That means plus and the bar. So R plus S plus Y. So this is what the Boolean expression that we got. Okay. Now after getting the Boolean expression, we have to go with the truth table. So the state function of truth table goes like this. Y, S, R. Y is the present state, SR are the input. So here how many combinations that we are considering? 0 to 7. So from 0 to 7 combinations. So out of here, if you are if you substitute Y, S, R over the expression, you will be getting the next state value. So if you consider, or else if you substitute Y, S and R values over this expression, my output or else my next state would be 0, 0, 1, 0, 1, 0 and 1, 0. Okay, so after getting this, what we need to do? We need to draw the Carnot map. So this is a table where we are representing the next state and as well as the present state, including the input. So my present state is Y, and I'm going with 0 or 1. Okay, either 0 or 1. And my next state, what? My next state would go as per the set and reset. That is 0, 0, 0, 1, 1, 0 and 1, 1. Right? So here my next state represented with Y. So when my input is, or else when my present state is 0, the next state is 0, 0. What happens? Where I can map is at 1, 0 position, I am getting the state is getting transisted. Then at present state 1, and where I can get see the combinations at 0, 0 and as well at 1, 0. Okay, so using the K map or else using the this particular table, we can able to easily draw the Carnot maps. The Carnot maps can be drawn with respect to the truth table or as a state table. And now, since we do not have any flip-flop, as it is asynchronous sequential machines, nowhere the flip-flops and latches have been used. So, since we don't have any flip-flops, but only combinational circuits, a state change can cause additional state changes. So, as we are not using any memory elements, so if you are finding or if you observe any changes in the state, so if you observe any changes, then that causes the additional state changes. If some state has been changed or if some transition has been occurred among the states, then you see that there is some causes. Okay, there is some cause has been occurred among the different states. So here, Y is nothing but the present next state. Next state is equals to present state, which is a stable state. And now a state is stable. Now we will see now whether the state is stable or unstable. How is, if a state is stable, if y of t is equals to, y of t plus delta. Okay, if this is nothing but a stable state. Why we are saying it is stable state? Because the next state depending upon the present state followed with some delay. This is a delay, right? So present state followed with some delay. When the state is when the next state depending on the present state along with some delay, then that sort of state is nothing but a stable state. And now we will see what is an unstable state. Unstable state goes like this. If y of t, if my next state is equals to, not equals to y of t plus delta, isn't it? That means what? If you see unsimilarities, or else if you see any discrimination not with respect to time, that means what? If my next state at t is equals to 0, my present state goes at t is equals to 0 plus something 1. So it is 0 and it is 1. So nowhere it is not related to each other. So there is an inequality, right? So this sort of state is nothing but the unstable state. So this sort of stable system is nothing but the unstable state system. So always remember that the next state in the asynchronous sequential machines, it depends upon the present state and followed with respect to some time. Then that system goes with the stable state system. And if the next state depends upon the present state, and if it is not equals to the time with respect to the delay, then that system is going to say as the unstable state. Okay, so as per this table, we can say that at y is equals to 0 only at if SR as 1 and 0, then this combination is correct, or else this combination has been occurred. So from this I can draw the state diagram. So this is a state diagram, and out of this state diagram, this is the state table. So from this this diagram has been written over with respect to this. So here we see the stable state and unstable state. So the stable state is nothing but y of t is equals to y of t plus delta t, whereas unstable state is y of t is equals to y of t not equals to y of t plus delta t. Okay, so this is how we are saying RS. If both are 0, what happens? If S is 0, what happens? The output goes as 1. If it is 0, the output goes as 1, and so the next state is 0. So here we see the same 0 and 0, which is a stable state, isn't it? So RS is 0, 0, SR is 0, 0, and my next state is 0, and my present state is 0. So we are achieving this combination. So this is a stable state, isn't it? And then when RS as 0, 1, when RS as 0, 1, what happens? Here we are getting the Y as 1, okay, Y as 1 and small y as 0, Y as 1 and small y as 0. So this is the combination that we are observing for the next state, that is 0, 1, and it is for 0, 0. And then if you observe for the unstable state as when R is as 0, 1. When R is as 0, 1, what happens? The Y as 1, Y as R is as 0, 1, R is as 0, 1, Y as 1, for example. R is as 0, 1, Y as 1, then we are observing that my expression is 1, then it goes like this. Okay, and then it goes like this. So this is all about the synthesis of the asynchronous sequential circuit. So here the stable state, next state is equals to present state are circled. Next state and the present state are circled. So here, and now we will see the terminology. So the terminology goes like this. When dealing with asynchronous sequential circuits, a different terminology is used. Okay, so when you're dealing with asynchronous sequential circuits, we use some different terminology that we can, if we compare the state table, we'll call it here as a flow table. Okay, when you're calling there as a truth table, here we'll be calling as a excitation table. So the terminology goes like this. A state table is also called as a flow table, and also a state assigned state table. Okay, so the state assigned state table is also called as the excitation table. So here these are the few flow tables for Moore and Mealy machines. Okay, you see this Moore and Mealy machines for the, Moore and Mealy machines as they are the examples for the synchronous sequential circuits. In the yesterday's class, we have discussed about the synthesis of synchronous sequential circuits. In the synchronous sequential circuits, they are categorized into two kinds of sequential machines. Those are, one is with respect to Moore and the other is Mealy. So here in this Mealy, we say that the output depends only on the present inputs, whereas in Moore, output depends on the present present input as well as the past output. Okay, so now we will see the flow table for Moore and Mealy. So this is the present state AB, and next state as per the SR latch 0001, 10 and 11, and these are the output. And similarly for the Mealy as well. So AB and SR as 0001, 10 and 11, and output goes in the Mealy. Why? Because the output depends on the present states and as present state input and as well as the past history outputs. So here we goes with 0001, 10 and 11. And now we will see as per the flow table, the excitation tables, or also as per the flow table, how I can draw the state diagram as well. So here I have only two states, A and as well as B. So here A and B, and my outputs are 0 and 1. Okay, so if A has the output 0, okay, if A has the output 0, what happens here is it goes with 0, 0, 0, 1 and 1, 1. If A is the output 0, it goes with 0, 0, 0, 1 and 1, 1, isn't it? And now moving on to the, if A itself is here in this A state, and now if the transition taking place from A to B, if the transition is taking place from A to B, then we see that A to B, then we see that SR latch as 10. So here, if it is moving on from A to B, so here we have B. So if it is moving on from A to B, so which state is going with respect to 1 and 0? Okay, and then goes with the state pertaining with the B state. And now we will see the B state. So B state is taking its next state transition with respect to 0, 0. Okay, with respect to 0, 0 and 1, 0, 0, 0 and 1, 0. Why? When the output is 1. When the output is 1, the transition or else the present state, the next state is observed with respect to the present state at 1, 0 and 0, 0. Okay, when the output is 1. So these are the outputs. 0 is the output. A are the state. This is nothing but the state. And now we will see from when with respect to the state B, the transition is if it is occurring from B to A. What happens is B to A, we see 0, 0, 0, 1 and 1, 1. So B to A. So here see 0, 1 and as well as 1, 1. From B to A, 0, 1 and as well as the 1, 1. So this is nothing but our state diagram we have drawn that with respect to the flow table. And now we will see the Mealy. So if you observe the Mealy here also we have the state. Okay, A is a state, B is a state. But here one thing we have to observe the difference between Moore and Mealy, saying that in the state diagram for Moore machines, we'll be writing the output. Okay, over with respect to the state. That like this, B/1. So B is a state, 1 is the output. A is a state, 0 is the output. Whereas coming to the Mealy, we don't represent any outputs in the circle. Circle itself is meant with respect to the state. So here we have A state and B state. And now if you observe A state and B state, with respect to the A state, at output 0, 0. Okay, at output 0. Okay, at output 0, how many states that we are transitions? 0, 0, 0, 1 and 1, 1. Okay, the output goes 0, 0, 0, 1 and 1, 1. When with respect to the output 0, with respect to the output 0, the state A goes with 0, 0, 0, 0, 0, 1 and as well as 1, 1. Isn't it? And then if the transition, the state is it's taking its position, or else if it is transition taking place from one state to another, that is from state A to state B. Okay, state A to state B. Then what happening is SR/Q. Okay, output SR/Q at 1, 0. At 1, 0, the transition from A to B is occurring at the output with respect to the next state input as 1, 0. Okay, and now we will consider with respect to the state B. And now if you observe with state B, what's happening with the output 1? When the outputs are 1, what happens? It is 0, 0, okay, 0, 0 and it is 0, 0 and 1, 0. So 0, 0 and 1, 0 when the 1 has the outputs. and not if the transition from B to A if it is taking place. Then how can we represent the A outputs with respect to the present state? See, if B to A means 0, 1 and as well as 1, 1. Okay, so 1, 1 and 0, 1. So this is how the transition between the different states from state 1 to state A to state B, and from state B to state A takes place. All that you have to understand, or else you have to remember between the Mealy and Moore machines is that when you are considering the Mealy machines, make sure that the output, it depends, the outputs of the next state will be considered as well. Whereas here in coming to the Moore machine, you have to remember that based on the output of the next state, the present state inputs and the next state output will be considered. Okay, so as per the excitation table or as a flow table, the state diagram is been written or is been drawn. And now if you observe here, we see don't care. Somewhere around here in the table, we are observing a small dash. Okay, so what is the dash means? Dashes are nothing but the don't care conditions. So don't care conditions has been chosen for the output decoder, since output changes directly after the state transition. So the output, it changes soon after the state transition. After the state transition, the output is changing. So when the output is changing soon after the state transition, then we are representing the don't care, that is a small dash. So this is how the representations will be made or else considered in this particular Moore and the Mealy machines. And now we will see asynchronous sequential circuits have similar structures as synchronous sequential circuits. So the asynchronous sequential circuits and synchronous sequential circuits, as I said you, they both are one and the same, but only the difference is the synchronous sequential circuits, they go as per the with respect to the time. Okay, they go with respect to the delays, whereas the asynchronous sequential circuits, here we see they go as not with respect to the time. So here, the asynchronous sequential circuits and the synchronous sequential circuits they are similar in structures, but only with one single differences. And instead of flip-flop, they have a delay block. So here, as we are discussing about the asynchronous sequential circuits, in the synchronous sequential circuits, only the difference that you can find here is the delay block. Okay, so the delay block can be observed. So here, if you observe, or else if you see here, this is a block diagram where we have the input signal, the next signal, followed with the asynchronous state machines that is considered, where we have the delays. Okay, where we have the delays represented with delta, and then finally the output decoder, where from the output decoder we have the output signal. So here in the this is a particular block diagram that you can observe. Previously we have discussed over there. So here this is a SR latch. Okay, this is a SR latch that we are considering. In this SR latch, the input signals are given as 0, 1. These are the input signals. Okay, and then the next state decoder goes on with the gates. Okay, we see that the gate delays. Okay, gate delays are initially ideal gates. We are considering the ideal gates where it's nothing but the 0, and also we are considering some delays. So SR as 0, 1, output goes with respect to 1, and here this is a delay, and based on the delay, the next state or the next state is observed based on the present state and as well as the delay. Okay, so if you observe here, this is a delay block. So we have a delay block. Similarly, with respect to the synchronous sequential machines, and now we will see the synthesis, as we are discussing about the synthesis of asynchronous sequential circuits. The synthesis is carried out using the following steps. So what are the steps that the synthesis follows with? So it has to create a state diagram according to the functional description. So the synthesis goes with the very first step is just to create a state diagram. First thing is to create the state diagram, how the state diagram is created with respect as per the functional description. Okay, and the second thing is create a flow table and reduce the number of states if possible. Also, it is similar like the synthesis of synchronous sequential machines. In the synchronous sequential machines itself, but the very first and the foremost thing is state diagram. So in the state diagram, if you are having more than the considered states, that means was instead of 4 states, for suppose if you are having any 5 or Now, if you're having any 7 or 8 states, what happens? If you're having any 7 or 8 states, there is a chance or there is a possibility of go for the reduction of the states. Okay, we can reduce the state. So similarly, in the synthesis of asynchronous sequential circuits as well, we can create a flow table. Okay, so first thing is create a state diagram. Create a state diagram. The next thing is create a flow table. In the flow table, based on the state diagram that you have, based on the state, okay, the state, if there are more number of states, there is a possibility of changing the states, reducing the state to minimum states. So here we can reduce the number of states if possible. And then assign codes to states and create excitation table. So assign codes to the state. So the third step is we have to assign codes to the state. Okay, assign the input and output codes to the state, followed and create the excitation tables. Okay, so after creating the excitation tables, the fourth step is determine the expressions or the transfer functions. So after coding or after deriving the excitation tables, and now followed with the Boolean expressions, or else followed with the transfer functions, or else the expressions, or else the expressions for the next state and as well as the output. Okay, and then we will construct a circuit that implements the above expressions. So here soon after the expressions, what we will do, the final step is we will construct the circuit. Okay, the circuit is been constructed based upon the above expression. Based upon the above expression, the circuit is constructed. So these steps, whatever we are seeing with respect to the synthesis of asynchronous sequential machines, the same steps we have in the synthesis of synchronous sequential machines as well. So there also we have the first and foremost step is creating a state diagram, and then reducing the state diagram if it is complicated, and then drawing a flow table or else a state table. In other words, in the synthesis of synchronous sequential circuits, instead of flow table, we are drawing the state table. And soon after the drawing the state table, we are going with the excitations of this table, and then followed with the Boolean expressions, or else the expressions with respect to the input and output. So from the expressions, we are going to draw the circuit diagram. Okay, so the circuit diagram is mentioned about, or the circuit diagram consists about all the gates. Okay, all the gates and as well as the all the gates with respect to the expressions that you got the previous one. Followed the step 5 is followed with respect to the step 4. Okay, so all the steps whatever we are observing in the synthesis of asynchronous sequential circuit, the same is observed in the synthesis of sequential circuits as well. And now we will see the example of simple parity generator. So here we will see the synthesis part of how a synchronous sequential circuit takes place by considering a single parity generator. So here in the single parity generator, as I said we have 5 steps to follow, right? So the step 1, the very step 1 is create a state diagram. So here by considering the single parity generator, we need to create a state diagram. So the state diagram, input we have X and output we are representing it with Z. Okay, input X and output Z, and Z is equals to 1 if the number of pulses applied to X is odd. If X is odd, then Z is equals to 1, where Z is nothing but the output. And also when Z is equals to 0, what happens is when the applied pulses are even. When the applied pulses are even, then Z goes with respect to 0. And now we will see the creating a state diagram with a single parity generator. So by considering the 4 states A, B, C and D. So here we have A, B, C and D, and as I said if it is odd, what happens? Z becomes, if it is odd, Z becomes 1, and if it is even, Z becomes 0. So here X is nothing but the input and Z is nothing but the output. So here A by 0, B by 1, C by 1, D by 0, A by 0. So here if you see Z is 1. So here we have the states B and C as 1, right? B and C as 1. So what happens here? This is nothing but the parity, or else this is nothing but the even, odd. For example, when Z is equals to 1, what happens? The number of pulses applied to X is odd, right? So when z is equals to 1, the number of parity upright is 1 odd, and then when z is equals to 0, so here we got the z is equals to 0, d and a. So here when z is equals to 0, then it is applied as even. When z is equals to 0, z is equals to 1, it is applied as odd. So similarly, this is a state diagram. We have 4 states A, B, C and D. When both are 0, okay, when both are 0, what happens? These are the even cases, and when both are 1, okay, when both are 1, these are the odd cases. Okay, that is nothing but the parity, serial parity. And now, second one is after state diagram, then we'll go with the flow table. Okay, so this is a flow table. This is a state diagram. We have 4 states A and B. When z is equals to 0, when z is equals to 1, when z is equals to 0, this is even, and when z is equals to 1, this is the odd parity. So as per this, we can write the present states are A, B, C, D. We have A, B, C, D, and z is the output. So here for A, my output is 0. So this is a state, and this is nothing but the output. So for A, my output goes as 0, and for B, my output goes as 1, and for C, my output goes as 1, and for D, output goes as 0. So based on the output and the present state, we will find out the next state, how it goes. So the next state has two things. One thing is x is equals to 0 and x is equals to 1. So when x is equals to 0, what happens is the state goes on with itself, A, okay, and but when x is equals to 1, what happens? It is taking a transition from A to B. So when x is equals to 1, it is taking a transition from A to B. This is achieved. And then coming to with respect to the state B. Okay, state B, and the present state is B. When output is 1, what happens? X is equals to 1. It is being with respect to the state here itself. Okay, when the output is 1, it is with respect to 1. And now from when x is equals to 0, what happens? When x is equals to 0, it is taking a transition towards the next state, that is C. This is C. That is when x is equals to 0, it is taking transition. But when x is equals to 1, it is when x is equals to 1, it is in this position itself. When x is equals to 1, it is in the same position B. When x is equals to 0, it is moving towards C. And then finally, the third one is considering the state C. So when state C, x is equals to 1, when the output is 1, what happens? It is, when x equals to 1, it is taking its transition towards D. Okay, towards D. But when x is equals to 0, when x is equals to 0, it is considered to be in its state itself. Okay, and then coming to the state D. So the state D here, when x is equals to 0, okay, when x is equals to 0, it is taking its transition. When x is equals to 0, it is taking its transition towards the state A. But when x is equals to 1, when the output is 0, when x is equals to 1, it is being itself in this own state. So when D is equals to D and D is equals to 1. That is how the state or else a flow table can be drawn with from the state diagram. So this is a step 1 and this is a step 2. Okay, we have done with step 1 and 2. And now we will see the assigning state codes. So the third step is assigning the state codes. So assigning the state codes is nothing but for A, we wrote A is equals to 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so we have total states as A, B and C, D. So A as 0, 0, B as 0, 1, C as 1, 0 and D as 1, 1. These are nothing but the codes that we are assigning to different states A, B and C and D. Okay, and then after assigning, we need to which encoding is good. So after assigning, we go with the encoding part. So here if you observe, suppose x is equals to 1. Okay, when x is equals to 1, y2, y1 is equals to 1, 1. So when for suppose x is equals to 1, x is equals to 0, 1, y2, y1, 0, 0, 0, 1, 1, 0 and 1, 1. Okay, so what happens here is 0, 0, 0, 1, 1, 0, 1, 1. So here, when x is equals to 1, y2, when x is equals to 1, y2, y1, y2 as 1, 1, somewhere around here. Okay, somewhere around here you will find a 1. So you see that x is towards 0 and y2, y1. X is towards 0 and y2, y1 as 0, 0. y2, y1 as 0, 0. That means somewhere around here. Okay, so this is what the possible parity bits, possible bits. Okay, the combination of bits can be appeared at 0, 0. When x is equals to 0, y2, y1 as 0, 0. When x is equals to 0, y2, y1 as 0, 0. So this is a possible matching state. And then when x is equals to 1, y2, y1 as 1, 1. y2, y1 as 1, 1. So this is one of the possible state. And then 1, 1 as 1, 0, 1, 1 as 1, 0, and 1, 1 as 0, 1, 1, 1 as 1, 0, and 1, 1 as 0, 1, and with respect to 1, 0, and with respect to 0, 0. So we will never reach 0, 0. Obviously, there is no point of reaching 0, 0 when you are considering your states to be as 1, 1. Okay, so bad encoding H2, HD as 2. Why? Because here we got these two states, but here we don't, there's no point of pairing. These are the individual bit at different states. These are the individual bits. Nowhere you have a chance of pairing. If you have a chance of pairing, then it would be good and fine, well enough. But here there is no chance of pairing. As we don't have any chance of pairing, what happens is the single parity bits, the single bits are observed over the 1, 1 and 0, 1. So we say that this sort of encoding is not good. It's a bad encoding. And now we will see the 0, 0, 0, 1, 1, 0 and 1, 1. These are nothing but the assigning the codes to the bits. And now we will see poor encoding. Why we are saying here it is a poor encoding? Because here HD is equals to 2. Why here HD is equals to 2? Why? Because if we are in 1, 1 under input W is equals to 1 and input changes to W is equals to 0, the circuit should change to 0, 0. Here, that means what? Here he is saying that if we are in 1, 1, if we are in 1, 1 under input W is equals to 1, and if this input changes as W is equals to 0, what happens is, if this input changes with respect to W is equals to 0, then the circuit may change to 0, 0. So, which is impossible. That's the reason we are saying that it is a bad encoding. Okay. Whereas this is a good encoding. Why? Because here the bits are individually located at different states. Okay, the bits are individually located at different states and there is no point of transforming from one state to the other state. So, here we can say that the good encoding goes with HD is equals to 1. That means only one bit at different stages can be observed. Here, he is giving just a note or else the assumption saying that if there is a chance of changing the input from 0 to 1, that means what, we can switch over from one state 0, 0, 1, 1 to 0, 0, which is not possible. So that's the reason we are saying that this is the encoding done as per this is not good when it compared to the other one. And now we will see the fourth one. Soon after drawing the flow excitation tables, we'll go with the Carnot maps. Obviously, the Carnot maps has to be drawn as per the flow table that we observed. So this is with respect to x, y2, y1 and 0, 0, 0, 1, 1, 0 and 1, 1. So as per this, the truth table or the Carnot maps have been drawn, and here we are observing the total pairing of the bits. How many pairs we can observe is pair 1, pair 2 and pair 3. So out of this pair 3, we see a common pair for 1, 1 at 0 and 1. We see a common pair with respect to 1, 1 at 0 and 1. So this is with respect to y2. And now we go with the y1. So out of, in this y1 also we see the pairing p1, p2 and p3. So out of these three pairings, we see one pairing is common, that is at 0, 1, 0 and 1. So this is what 0, 1 is with respect to 0 and 1. So these are the two common pairings with respect to y1 and y2. These two are y1 and y2 are nothing but the next states. And so out of this y1 and y2, again we can draw the Carnot maps, where here we are getting a single pairing 1, 1. So where we are observing 1, 1 at y1 at y1. Okay, so z is nothing but the output. output we got the pairing at z is equals to y1. So the red circles are needed to avoid hazards. Okay, so avoid hazards is nothing but in order to avoid the consequences, severe consequences, the important thing that we have to consider is considering the red marked bits. Okay, so in order to avoid the hazards, always remember, in order to avoid the consequences, severe consequences, always we have to consider the actual pairing. Okay, this one has got paired and this one has got paired. So the thing is, we have to pair, or else we have to consider this bits 1 and 1. So you have to consider only these bits 0, 1 of 0 and 1, but not as 1 and 1. Okay, if you are not considering this one, then the severe consequences has been occurred. So in order to avoid those sort of hazards, always remember that considering the red marked bits first. And then, so till part 4, or else till step 4, we have done with the drawing of Carnot maps. Then after this, okay, after step 4, what is a step 5? Step 5 is about step 5 is expressions. Obtaining the step 5 is obtaining the expressions, and step 6 is drawing the circuit diagram, isn't it? So the 6 steps we have observed. So till step 4, this is what we got. We got the Boolean expressions with respect to y1, y2, and then after obtaining the expressions, so this goes to step 5. So after obtaining the expressions, the final stage or the final step in the synthesis of asynchronous sequential circuits, the step 6 is drawing the circuit diagram. So out of this, we can draw the circuit diagram using the basic gates. Okay, x and y, x, y. Now x and y1, x and y1 given to y2, y1 and given to x, y2. Okay, so this is about y2. Similarly, I can draw for y1. So y1 is x, y2 and y2, y1, and then x, y1. So this is about y1. And then we got a final output expression with respect to z is equals to 1. So for this, there is no need to draw the circuit diagram. So this is nothing but the step 6. Step 6. So this is all about the synthesis of asynchronous sequential circuit. So today's topic, we have discussed what is the difference between the synthesis and synthesis of asynchronous sequential circuit and as well as sequential circuits. And in the synthesis of asynchronous sequential circuits, we got to know the different terminology based on the we got to know different terminology when you compare both the synthesis of synchronous and asynchronous sequential circuits, and also the step how to synthesize a given problem, how to synthesize. So using totally 6 steps we can able to synthesize. First one is by considering the state diagram, and then following with the state table, and then following with the state excitation table, and then drawing the Carnot maps, obtaining the expressions, and then finally drawing the circuit diagram. So this is how the synthesis of the asynchronous sequential circuit takes place. In the asynchronous sequential circuits, we are not using any memory elements like flip-flops and latches. If you are using any memory elements like flip-flops and latches, all you have to face the consequences of metastability. Okay, and then finally, by considering a single parity generator, we could able to sort out, or else we could able to synthesize the asynchronous synthesis of asynchronous sequential circuits. So I hope you all understood well, and that's it for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.